Hello everyone, and welcome back. In this chapter, we're going to explore some of the core network services that keep enterprise networks running smoothly. These services operate behind the scenes, but without them, modern networks simply wouldn't function. The Cisco iOS operating system includes many built-in network services designed to improve scalability, automation, and network management. These services, known as IP services, provide essential functionality within modern networks. Examples include Dynamic Host Configuration Protocol for automatically assigning IP addresses to devices, Domain Name System for translating host names into IP addresses and monitoring protocols that improve visibility and management across the network. In this chapter, you will learn how to configure network time protocol to synchronize device clocks, implement DHCP on Cisco routers to automatically distribute IP configuration to clients, and understand how DNS enables devices to locate resources across the internet. You will also explore Simple Network Management Protocol and Syslog, which help administrators monitor, manage, and troubleshoot network devices. Finally, we will introduce quality of service and how it can be used to prioritize important network traffic and improve overall performance. Topics covered in this chapter: understanding NTP, understanding DHCP, DNS, understanding the benefits of using Syslog, SNMP, and quality of service traffic classification. Time plays an important role in networks because it allows administrators to track when events occur. Devices such as routers, switches, servers, and security systems generate timestamps that record when actions happen. These timestamps are essential for logging, monitoring, security investigations, and troubleshooting. On an enterprise network, maintaining accurate and synchronized time across all devices is critical. Cisco devices constantly generate syslog messages that report events such as interface changes, configuration updates, and security alerts. If devices have incorrect or inconsistent time settings, logs from different systems will not align, making it difficult to trace the sequence of events during troubleshooting or incident analysis. Cisco iOS devices maintain time using an internal system clock, which starts when the device boots. By default, Cisco devices do not automatically use the correct time and date. Instead, the clock begins at UTC Monday, March 1st, 1993, meaning it must be configured manually or synchronized with a time server. There are two ways to configure time on a Cisco device: manual configuration and network time protocol, NTP. Manual configuration uses the following command in privileged mode: clock set, hour, minutes, seconds, month, day, year. While this method works, it is not practical for large networks because each device must be configured individually and clocks can drift over time. This can lead to inaccurate logs and inconsistent timestamps between devices. To check the current time on a Cisco device, use show clock. In larger networks, network time protocol is used to automatically synchronize clocks across devices. Routers and switches can connect to NTP servers and synchronize their system clocks, acting as NTP clients. NTP operates using UDP port 123. NTP uses a hierarchical structure called stratum levels to represent the distance from the most accurate time source. So stratum 0, authoritative time sources. Stratum 1, servers directly connected to stratum 0 devices. Stratum 2 to 15, devices that obtain time from higher level servers. A lower stratum number indicates a device is closer to the authoritative time source, while a higher number means it's further away. Stratum levels range from 0 to 15. Any device operating at stratum 16 is considered unsynchronized and cannot provide reliable time. Every device on a network requires an IP address in order to communicate and share resources. Network administrators typically assign static IP addresses to infrastructure devices such as routers, switches, firewalls, and servers. Static addresses remain unchanged, making it easier for administrators to remotely access and manage these devices. However, most networks contain many end devices such as laptops, smartphones, and workstations that frequently move between locations. Assigning static IP addresses to these devices is inefficient because their network settings may not match the addressing scheme of the new location, requiring manual configuration. As networks grow, manually configuring static IP addresses for every device becomes time-consuming and prone to human error. Administrators may accidentally assign duplicate IP addresses or incorrect subnet masks, which can cause connectivity issues. To solve this problem, networks use Dynamic Host Configuration Protocol. A DHCP server automatically assigns IP configuration settings to devices when they join the network. These settings typically include IP address, subnet mask, default gateway, and DNS server address. Using DHCP simplifies network management by automating IP address assignment and ensuring devices receive the correct configuration. Cisco iOS routers can also function as DHCP servers, allowing them to distribute IP configurations to clients on a network. This feature is particularly useful in small networks or branch offices, where deploying a dedicated DHCP server may not be necessary. When a device connects to a network, it automatically looks for a DHCP server to obtain an IP configuration. The DHCP server assigns an IP address lease, which is valid for a specific period of time. The DHCP process follows 4 main steps, often remembered as DORA. DHCP Discover. When a client joins the network, it sends a DHCP Discover message as a broadcast to locate a DHCP server. Destination MAC, source port, destination IP. Because the client does not yet have an IP address, the message is broadcast across the network. Number 2, DHCP Offer. When a DHCP server receives the Discover message, it responds with a DHCP offer containing an available IP address and configuration details. The offer includes information such as IP address, subnet mask, default gateway, DNS server, and lease time. Then number 3, DHCP Request. The client sends a DHCP request message to accept the offered configuration. This message is also broadcast so that all DHCP servers know which offer was accepted. Number 4, DHCP Acknowledgement. The DHCP server verifies the IP address is available, often by sending a quick ICMP ping and then replies with a DHCP acknowledgement. The DHCP server verifies the IP address is available and then replies with a DHCP acknowledgement. This confirms the lease and allows the client to begin using the assigned IP address. Lease renewal. DHCP addresses are leased for a limited time. Before the lease expires, the client sends a DHCP request to renew the lease. If the server approves the renewal, it replies with a DHCP acknowledgement and the client continues using the same IP address. Configuring DHCP on a Cisco iOS router is straightforward and allows the router to automatically assign IP configurations to clients on the network. Before creating a DHCP pool, it is recommended to exclude IP addresses that should not be distributed by the DHCP server. These typically include addresses used for routers, servers, or other devices with static IP configurations. So the commands used, and this excludes a single IP address, IP, DHCP, excluded address, IP address, and this to exclude a range of addresses, IP, DHCP, exclude address, start address, and end address. A DHCP pool defines the configuration information that will be assigned to DHCP clients, such as IP addresses, gateway, and DNS settings. These are the steps to configure a DHCP pool. So to create the DHCP pool, IP, DHCP pool, pool name. To define the network and subnet mask, network, network ID, and subnet mask. Specifying the default gateway, default router, IP address. Define DNS servers, DNS server, IP address, and specify the domain name, domain. Multiple DHCP pools can be configured on a single Cisco router to support multiple networks or subnets. To disable DHCP services on a Cisco router, use No Service DHCP. To enable DHCP services, service DHCP. A Cisco interface can also be configured as a DHCP client using IP address DHCP. In the next section, you will learn how DHCP Relay allows DHCP requests to reach servers located on different networks. In large organizations, servers such as DHCP, DNS, and file servers are often located in a central data center or a separate subnet. Clients on other networks still need access to these services. When a device connects to a network, it sends a DHCP discover broadcast to locate a DHCP server. However, routers do not forward broadcast traffic by default. If the DHCP server is on another subnet, the router blocks the broadcast, preventing the client from receiving an IP address. To solve this problem, Cisco devices use DHCP Relay. DHCP Relay allows a router to forward DHCP broadcast messages to a DHCP server on a different subnet. This is configured using the IP helper address command. So here's an example configuration. So router 1, interface, gigabit ethernet 0/0, IP helper address 172.16.1.2, and exit. When configured, the router receives the DHCP discover broadcast from the client and forwards it as a unicast message to the DHCP server. Important points: routers block broadcasts by default. DHCP Relay forwards DHCP requests across subnets, and the IP helper address command should be applied to the interface facing the DHCP clients. Using a DHCP Relay allows organizations to centralize DHCP servers while still providing IP configuration services to multiple networks. So let's look into DNS. When you enter a website such as www.cisco.com into a web browser, the computer must determine the IP address of the server hosting that website. Since devices on a network communicate using IP addresses, the system must translate the human-readable name into the correct address. Remembering the IP address of every website would be extremely difficult, and addresses can change over time. To solve this problem, the domain name system was created. DNS is a network service that translates host names or domain names into IP addresses, allowing users to access websites using easy-to-remember names. For example, instead of remembering a numeric IP address, users can simply enter www.cisco.com and DNS will resolve it to the correct server address. Before DNS existed, computers relied on a hosts file that manually mapped host names to IP addresses. When a user attempted to access a website, the system checked this local file to determine the correct IP address. However, maintaining and updating hosts file for the growing internet quickly became impractical. DNS servers replaced this method by maintaining centralized databases of domain records. Each DNS server manages records for specific domains and top-level domains, TLDs, such as .com, .net, and .org. A domain name includes a name and a TLD, such as cisco.com. A fully qualified domain name includes the host name and domain, specifying the exact device, such as www.cisco.com. Using DNS allows networks and the internet to efficiently map human-friendly names to IP addresses, making it much easier for users to access online resources. The domain name system operates using a hierarchical structure made up of multiple levels of DNS servers. At the top of this hierarchy are the DNS Root Servers, which help direct DNS queries to the correct domain servers. Root DNS servers contain information about top-level domains such as .com, .net, and .org. For example, the .com root servers contain records that point to domains such as cisco.com and its subdomains like community.cisco.com. When a device needs to resolve a hostname, it sends a DNS query to its configured DNS server. If the server has the record, it returns a DNS reply containing the corresponding IP address. The client can then use that IP address to communicate with the destination server. If the DNS server does not have the requested record, it can query other DNS servers within the DNS hierarchy until the correct record is found, and then return the result to the client. Many organizations and users rely on public DNS services that provide fast and reliable name resolution. Some popular public DNS providers include Cloudflare DNS, Cisco Open DNS, and Google Public DNS. Through this hierarchical system and cooperation between DNS servers, DNS ensures that host names can always be resolved to the correct IP addresses across the internet. DNS servers store different types of DNS records, each used for a specific purpose in mapping domain names to services or information. Common DNS record types include A. Maps a hostname to an IPv4 address. Quad A. Maps a hostname to an IPv6 address. MX. Identifies the mail exchange servers for a domain. NS. Specifies the authoritative name servers for a domain. CNAME. Creates an alias that points one hostname to another. SOA defines the start of authority for a domain and contains domain administration information. SRV specifies service location records for specific services. PTR performs reverse DNS lookup, mapping an IP address to a hostname. RP specifies the responsible person for the domain. HINFO provides host information such as operating system or hardware details. And text stores text information often used for verification or security records. For example, when a computer needs to determine the IPv4 address of www.cisco.com, it sends a DNS query requesting the A record from a DNS server. To troubleshoot DNS issues on a client device, administrators often use the NS lookup utility, which is available on both Windows and Linux systems. This tool allows users to query DNS servers and verify that domain names resolve to the correct IP addresses. Network devices such as routers, switches, and firewalls generate log messages whenever events occur. These messages provide administrators with details about both critical and non-critical events, helping them monitor network activity and troubleshoot issues. Syslog is both a protocol and a standard used for generating, formatting, and managing system log messages on network devices and servers. Syslog uses UDP port 514 to send log messages to a centralized Syslog server. Implementing proper syslog management provides several benefits: improved monitoring and troubleshooting by tracking events across network devices, severity-based logging, allowing administrators to send only important log levels to a server, and centralized log collection, making it easier to analyze and correlate events across the network. By default, Cisco devices display log messages on the console line. However, logs can also be stored in the device's internal buffer, VTY sessions, and a centralized syslog server. Using a centralized syslog server is recommended because it collects logs from multiple devices in one location. This allows administrators to view events in chronological order and quickly identify the sequence of events during troubleshooting or security incidents. Each syslog message includes two key elements: a facility and a severity level. The severity level indicates how critical the event is and ranges from 0 to 7, with 0 being the most severe. So let's go through this chart here. You have level, name, and description. Level 0, emergency. This means the system is unusable. Level 1, alert, immediate action required. 2, critical conditions. Level 3, error conditions. Level 4, warning messages. Level 5, notification, normal but significant events. 6, general informational messages. And 7, debugging messages. A simple phrase used to remember the levels is: every awesome Cisco engineer will need ice cream daily. Cisco devices generate syslog messages using the following format. Here's a breakdown of the fields: sequence number, unique number assigned to each log message, enable with service sequence numbers. You've got timestamp, date and time of the event, enable with service timestamps. Facility, this indicates the source or subsystem. Severity, numeric level from 0 to 7, representing the seriousness of the event. Mnemonic, short identifier describing the event, and description, detailed explanation of the event. Here's an example syslog message. You have the timestamp, facility, severity, mnemonic, and description. And here's an example with sequence number. By default, Cisco logs may not include the full date. To include timestamps in logs, use service timestamps log date time. Organizations typically send logs to a centralized syslog server for easier monitoring and analysis. Popular syslog solutions include QoS Syslog Server and PRTG Network Monitor. Centralized logging allows administrators to analyze events across multiple devices and track issues in chronological order. Simple Network Management Protocol is used by network administrators to monitor, manage, and troubleshoot devices on an IP network. It allows administrators to collect performance data and manage devices such as routers, switches, servers, workstations, and security appliances. SNMP operates through three main components: SNMP Manager, SNMP Agent, and Management Information Base. Together, these components form a network management system. The SNMP Manager is the application running on the administrator's computer. It communicates with network devices to collect information or make configuration changes. The manager sends SNMP GET messages to request information and SNMP SET messages to modify device configurations. The SNMP agent runs on the network device itself, such as a router or switch. It communicates with the SNMP manager, gathers device information, and executes instructions sent by the manager. The Management Information Base acts as a database that stores information about the device's operational status, such as CPU usage, memory utilization, interface statistics, and network performance metrics. To access device information, an administrator uses an SNMP manager and connects to the device using its IP address and authentication credentials, commonly known as a community string. If authentication is successful, the administrator can monitor the device and retrieve performance data. SNMP uses UDP port 161 for communication between the SNMP manager and agent. SNMP trap messages are sent from the agent to the manager using UDP port 162. SNMP uses several message types: GET, SET, and TRAP. GET retrieves information from a device. SET modifies device configuration, and TRAP, notifications sent by the agent when an event occurs. SNMP managers present this information through graphical dashboards, allowing administrators to view metrics such as CPU load, memory usage, latency, and packet loss. This data helps organizations generate reports, establish network baselines, and identify performance issues. SNMP typically gathers data through polling, where the manager periodically requests information from devices. The polling interval can be adjusted depending on how quickly administrators need to detect issues. However, very frequent polling may increase network traffic, so intervals must be configured carefully. There are three main versions of Simple Network Management Protocol: SNMP version 1, SNMP version 2C, SNMP version 3. SNMP version 1 is the original version and provides very limited security. It does not include authentication, user privileges, or encryption between the SNMP manager and agent. SNMP version 2 improves performance and uses community strings for access control. These strings act as simple passwords that allow the SNMP manager to communicate with the device. However, SNMP version 2 still lacks strong security because it does not support authentication or encryption. SNMP version 3 introduces significant security improvements. It supports user authentication and encrypted communication between the SNMP manager and agent. Authentication can use MD5 or SHA, while encryption can use DES or AES, making SNMP version 3 the most secure version. SNMP version 1 and 2 rely on community strings to access the MIB on network devices. The two main types are read-only, allows the manager to view information in the MIB but not make changes, And read-write allows the manager to read information and modify device configuration. In the next section, you will learn about the Management Information Base and its role in SNMP operations. The Management Information Base is a database used by SNMP that stores information about the components and operational state of a network device. It contains a collection of object identifiers, which represent specific variables that can be monitored or managed on the device. Each OID corresponds to a particular piece of information or function on the device. For example, an OID may represent interface statistics, CPU usage, memory utilization, or other device parameters. When an SNMP manager needs to retrieve or modify information on a device, it references the appropriate OID in the MIB. The MIB is structured as a hierarchical tree with multiple branches and sub-branches representing different device components and functions. This structure allows the SNMP manager to locate specific information about the device efficiently. Using the OID values defined in the MIB, the SNMP manager communicates with the SNMP agent to gather statistics or modify configuration settings on the network device. Cisco provides a useful tool called the Cisco SNMP Object Navigator, which helps administrators translate OIDs into readable object names and descriptions. In busy networks, large amounts of traffic can lead to network congestion, similar to traffic jams on a busy road. When too many packets attempt to use the same network link, delays occur, and some packets may even be dropped. Enterprise networks carry many types of traffic each day, including voice calls, video conferences, web browsing, email, file transfers, and business applications. When congestion occurs, all traffic competes for the same bandwidth. This can cause slow response times, delays, and poor user experience. Quality of service helps solve this problem by allowing network engineers to classify and prioritize traffic. Time-sensitive traffic such as voice and video can be given higher priority over less critical traffic like web browsing or email. Routers and switches process thousands of packets per second. Incoming packets are temporarily stored in buffers until they can be forwarded. However, these buffers are limited in size. If too many packets arrive and the buffer becomes full, new packets may be dropped, which increases delays and reduces performance. Queuing increases network delay, and congestion leads to higher latency. This is particularly problematic for real-time applications such as voice over IP and video conferencing. These applications often use UDP, which is faster and creates less overhead than TCP. However, UDP is connectionless and does not guarantee packet delivery, meaning packets lost during congestions are not retransmitted. Using QoS, network devices can prioritize critical traffic to ensure important services such as voice and video maintain acceptable performance even when the network is congested. QoS mechanisms are only applied when network congestions occur. In networking, several key terms are used to describe network performance and transmission quality. Understanding these concepts is important when implementing quality of service to manage traffic effectively. Bandwidth refers to the amount of data that can be transmitted over a network link in a given period of time. It is typically measured in bits per second. Modern network interfaces such as Gigabit Ethernet can support speeds of up to 1 gigabits per second or higher. Congestions occur when the volume of network traffic exceeds the available bandwidth. When too many packets arrive at a network device, its queue can become full, causing delays and packet drops. QoS is often implemented at these congestion points to manage traffic more efficiently. Delay, also known as latency, is the time it takes for a packet to travel from the source device to the destination. High latency can cause slow response times for applications and services. Jitter refers to the variation in packet delay. In a stable network, packets arrive at consistent intervals. However, congestion, poor queue mechanisms, or interface issues can cause packets to arrive at irregular times, which negatively affects real-time applications such as voice and video. Packet loss occurs when packets are dropped because buffers are full or network errors occur. excessive packet loss can disrupt communication. When using TCP, lost packets are retransmitted until acknowledged. However, UDP does not retransmit lost packets, making packet loss especially problematic for applications that rely on UDP, such as voice and video. Modern networks carry many different types of traffic. With the growth of cloud services, remote work, and online collaboration, the amount of voice and video traffic on enterprise networks has increased significantly. Each traffic type behaves differently and has different requirements for reliable transmission. Voice traffic, such as VoIP calls, is generally predictable and steady, but is highly sensitive to delay and packet loss. Since voice typically uses UDP, lost packets are not retransmitted, which can cause noticeable issues such as missing words, static, or broken audio. For acceptable voice quality, networks should follow these guidelines. Latency, less than 150 ms. Jitter, less than 30 ms. Packet loss, less than 1%, and bandwidth requirement, minimum of 30 kilobits per second. Because of its sensitivity to delay and loss, voice traffic should be given the highest priority using QoS. Video traffic requires significantly more bandwidth than voice and can be inconsistent in packet size and timing. Like voice, video often uses UDP, which means packet loss is not retransmitted. Without QoS prioritization, video streams may experience blurry or distorted images, out of sync audio and video, and interrupted playback. Recommended network conditions for video traffic: latency less than 400 ms, jitter less than 50 ms, packet loss less than 1%, bandwidth requirement minimum 384 kilobits per second. Because video packets vary in size and timing, video traffic can be less predictable and less resilient than voice traffic. Data traffic includes applications such as web browsing, email, and file transfers. These applications usually rely on TCP, which ensures reliable delivery. If packets are lost during transmission, TCP automatically retransmits them until the destination acknowledges receipt. This makes data traffic more tolerant of packet loss than voice or video. However, some data applications, especially HTTP and HTTPS traffic, can consume large amounts of bandwidth. If TCP traffic dominates the network, time-sensitive UDP traffic, such as voice and video, may be delayed or dropped. Using QoS policies, administrators can prioritize critical traffic types to ensure important applications maintain good quality of experience for users. Network devices use queuing algorithms to determine how packets are processed and forwarded when multiple packets arrive at an interface. These algorithms help manage traffic during periods of congestion. First in, first out is the simplest queuing method. Packets are processed in the exact order they arrive, following a first come, first served approach. There is only one queue, and all packets are treated equally with no prioritization. While first in, first out is simple, it does not perform well in congested networks because critical traffic cannot be prioritized. WFQ, weighted fair queuing, improves traffic management by distributing bandwidth fairly across different traffic flows. The algorithm classifies packets into flows or conversations and assigns weights to determine how bandwidth should be shared. Traffic classification can use information such as the type of service field in the IP packet, where DHCP markings are located. One limitation of WFQ is that it does not work well with encrypted traffic tunnels, since encryption hides the packet information required for classification. Class-based weighted fair queuing, CBWFQ, is an extension of WFQ that allows administrators to define specific traffic classes using criteria such as network protocols, access control lists, and input interfaces. Each traffic class is assigned its own FIFO queue, along with configurable characteristics such as bandwidth allocation, packet limits, and priority weights. During congestion, each class receives its configured share of bandwidth. Low latency queuing, LLQ enhances CBWFQ by introducing strict priority queuing. This allows critical traffic such as voice and real-time communications to be transmitted before packets in other queues. By prioritizing delay-sensitive traffic, LLQ helps reduce latency and jitter, improving the quality of real-time services. When implementing quality of service, network engineers typically choose between three main QoS policy models: best effort, integrated services, differentiated services. The best effort model provides no guarantees for packet delivery, delay, or priority. All traffic is treated equally, regardless of importance. A simple analogy is the standard postal service. Letters are delivered without prioritization of delivery confirmation. The advantages: very simple to implement, highly scalable, and requires no QoS configuration. The disadvantages: no guarantee of packet delivery, packets may arrive out of order, and no prioritization for time-sensitive or critical traffic. Best effort is still the most common traffic model on the internet, where all packets are handled equally. Integrated services. Integrated services was designed to support real-time applications such as video conferencing and interactive media. It provides end-to-end QoS guarantees between a source and destination. Integrated services operates using a connection-oriented approach where applications request specific resources such as bandwidth or delay limits for a data flow. Each individual traffic stream is called a microflow. To reserve network resources, integrated services uses the resource reservation protocol. If sufficient resources are unavailable along the path, the data transmission does not begin. The advantages: provides end-to-end resource reservation and allows per-flow quality of service control. The disadvantages: resource intensive and not scalable in large networks due to maintaining state information for each flow. Differentiated services is a scalable quality of service model that classifies traffic into groups rather than managing individual flows. Traffic is marked and characterized into classes, and network devices apply QoS policies based on those classifications. Critical traffic such as voice and video can receive low latency and higher priority, while less important traffic such as web browsing or email can be treated as best effort. The advantages: highly scalable for large networks, efficiently prioritizes time-sensitive traffic, and simpler implementation compared to IntServe. The disadvantage: does not provide strict end-to-end quality of service guarantees. In diff-serve networks, routers classify incoming traffic into classes and apply appropriate quality of service policies to manage bandwidth and prioritize important traffic. Quality of service is implemented using several mechanisms that help network devices identify, prioritize, and manage network traffic during congestion. Classification is the process where a network device examines packet fields to identify the type of traffic. QoS tools are applied on device interfaces, allowing routers and switches to inspect packets and determine how they should be handled. Once packets are classified, they are placed into a queue for the outgoing interface. A scheduler then determines which packet should be transmitted based on the priority assigned to the traffic type. Marking modifies certain fields in a packet header to indicate the packet's priority level. This allows other network devices along the path to easily recognize and classify the traffic. Important note: the differentiated services code point is a 6-bit field in the IP header used for quality of service marking. At layer 2, class of service is used for marking. Cisco also provides a tool called Network-Based Application Recognition, which helps identify and classify application traffic automatically. Queuing manages how packets are stored while waiting to be transmitted through an interface. When multiple traffic classes exist, packets are placed into different queues based on their classification. A scheduler determines which queue is served first when the interface becomes available. Cisco devices commonly use a round-robin scheduling algorithm, which cycles through queues and sends packets from each queue in turn. Tools such as class-based weighted fair queuing ensure each traffic class receives a configured percentage of bandwidth. Policing and traffic shaping are used to control the rate of traffic, often at the WAN edge of a network. Policing drops packets that exceed the configured bandwidth limit. Shaping temporarily stores excessive packets in a queue and sends them later to smooth traffic flow. Both methods help ensure traffic stays within defined bandwidth limits. Congestion avoidance techniques reduce packet loss by proactively discarding certain packets before the network becomes fully congested. This mechanism helps control traffic flows, particularly in TCP connections, preventing network buffers from becoming completely full. Summary. In this chapter, we explored several essential IP services that improve the efficiency, management, and reliability of enterprise networks. You learned the importance of accurate timekeeping and how network time protocol synchronizes device clocks across the network. We also examined DHCP, which automatically assigns IP configurations to devices, and domain name system, which translates host names into IP addresses to simplify network communication. We covered network management tools such as Simple Network Management Protocol, which allows administrators to monitor and manage network devices, and Syslog, which enables centralized login and better visibility of network events. Finally, we introduced quality of service and how it helps classify, prioritize, and manage traffic to ensure that time-sensitive applications like voice and video perform reliability during network congestion. By completing this chapter, you now have a stronger understanding of the core IP services used in enterprise networks, which are essential skills for real-world networking and the CCNA certification. In Chapter 11, Exploring Network Security, we will begin learning how to protect networks from cyber threats and implement security mechanisms to safeguard enterprise infrastructure. I hope you enjoyed this chapter and enjoying the full series. I'm CyberEd, and I will see you in the next one. Peace.